El diseño integrado en este gran despacho colaborativo y multidisciplinario que es SOM en Nueva York. No, you're from San Francisco, right?
San Francisco.
Okay.
Yeah, yeah.
Bueno.
It's all one. All
yes,
one.
Yes. Thanks.
Well, it's an honor to be here. Thank you to the College of Architecture and the opportunity to talk to you today about invention. And yes, okay. I'm a structural engineer, and in our firm, SOM, we practice as engineers and architects together. And we think about design from a perspective that comes from organic forms, from art, from experimentation. So working with universities to develop new ideas, whether they're tall buildings or short buildings, what can we do to change the way we think about design? And most importantly, what can we do to change the path, which we believe is a destructive path on the environment? Cities are developing around the world at a rapid pace, whether it's in Mexico or Shanghai. And the impact of these cities on the environment is substantial. So the use of natural resources, the embedded carbon that's part of the buildings as we build them, and the carbon that's emitted when we operate these buildings are all creating a great impact on the global both economic and most importantly climatic situation. The last century, we saw climate change in temperature of 1.5 degrees. We expect that in this next century, it'll accelerate. So greater temperature change. When we build buildings, most of the buildings that are of great scale, let's say at least 20 stories or more, the amount of embodied carbon in the structure, in the building, the day we built it, most cases takes 20 years to be overcome by the operational carbon from mechanical systems and lights and so forth. So the day we build, in many cases, is just as important or more important than the operation of our buildings.
Celestial event. No words can describe poetry. I should have said beautiful. So beautiful. Beautiful. So beautiful. So beautiful. I had no idea.
The image on the right is one of two places in the world that houses every seed known to mankind, just in case. Disruption. Disruption of ideas, inventions that change the way we think, whether it's transportation or buildings, is what I would argue is the next step for us to take in terms of designers, builders, to change the place that we're having great impact on. And we do it in incremental steps. In buildings, it's an idea of creating form that is efficient, creates great architecture, we hope. Ideas that are stable, but ideas that take forces and allow forces to flow around a form, to balance gravity loads against seismic loads and wind loads. So taking the helix in this case and allowing the forces of gravity to flow around the entire form to help resist the building from overturning in wind or seismic events. The idea of balancing the placement of material and making the building as efficient as possible. That's our goal. And then creating great spaces. Spaces where people use and are inspired, whether it's at the base of the building or it's how we interact with the building throughout the elevation of the building and how we celebrate structure as part of the experience. That's our hope, to take the ideas that are fundamental to design and create something that is really unique. The Fibonacci sequence is something that a lot of us have studied. Many people think of it as an incremental series of numbers, but it's far more powerful than just a numeric exercise. The relationship of numbers is interesting. There's a constant that emerges. So the relationship between 13 and 8, for example, is the constant that you see at the top, 1.618. And if you continue out on the Fibonacci sequence, you'll find that, like pi, the number converges. It becomes much more accurate. So what does it mean to us as designers? Well, it means that it's a search for where it exists in other places. So in nature, the way plants grow, trees, small plants, is impacted by this constant. It's impacted by the geometric lengths of arms of the tree. It's impacted on the numerics that help us describe growth. The leaf in the northern hemisphere on most species of plants points south first. Why? Because that's where most of the sun is seen throughout the year. But then the question is, where does the next leaf point? Well, in the northern hemisphere, the next leaf will point 137.5 degrees off of the first leaf. And you wonder, well, why is it 137.5 degrees? Well, it's because every single leaf that sprouts after the first leaf will never cover a previous leaf. And you can do that. You can take 137.5 and plot it on a circular pattern. No dot will ever cross a previous dot. So here's the factor again. Well, if you take 137.5 degrees and you relate it to a 360-degree circle, you find that the constant reappears. It's not random. It's in all of us. It's in the way the hair on the top of our heads grow. It's the way the universe has been created. It's the way plants grow. And maybe it's the way we design buildings. So if we take the Fibonacci sequence and we allow it to radiate vertically, perhaps we can create framing systems of structures that respond in a way that's not linear. It's greater density at the base where the demands are highest, least density at the top, and you can see the orientation of the bracing changes as we go over the height of the building. We're finding that with this type of philosophy and design, we can save 20% of the material in that frame. We're looking at buildings not like beams and columns. We're looking at them as forms, as geometric forms, whether they're volumes or in this case, 4 planes. And what we find when we apply load to these forms, that bracing patterns come out that emerge that are much different than we're normally used to. You would think that the bracing pattern for this tall building would be concentric. In fact, it's not. It's a high-waisted brace. This is the most efficient way to resist lateral loads for this tower, for those points of support at the base. 3/4 to 1/4. It's not symmetrical. And we're taking these optimization platforms, and we're creating first the theory on the left, and then we're interpreting the architecture from the engineering. So it's not such a sterile response. It's a much more organic response. And it's a progression. It starts with the basic idea, the form on the left, the initial engineering idea that's the most efficient, that's in the middle, and then there's a hybrid consideration. Taking that initial idea, and in this case, as the chassis, and then stretching it over the height of the building to create something that we believe is organic and beautiful and efficient in terms of the way forces are managed. But in tall buildings, in areas of high seismicity, it's a question of stiffness and softness. Stiffness related to winds and daily events, and softness related to the earthquake when it comes. Dissipating energy when you need to. So creating fuses within these tall building structures is the answer. So we think we've discovered that this combination of stiffness and softness is the answer to tall building design in areas of high seismicity, like here in Mexico City. So buildings in the future, we think, are going to look much different. The Hancock building on the left, a very efficient design, concentrically braced, and the building on the right in China, where this organic pattern emerges from the most efficient placement of material in that structure. You can take these ideas and turn them on a horizontal. So it doesn't need to be a tall building. It could be a bridge, or it could be a long span building. And if you simply mirror the idea around the center point with 2 points of supports at the outside, you find that you create a structure that takes the tall building philosophy and puts it on the flat. And it takes that 3/4, 1/4 geometry of bracing in the tall building, and it puts it into the frame of the bridge. This is a helical, it's a circular or an elliptical pattern. You could use it on any geometry. It could be square. You can do it in concrete or in steel. But you can see that these bridges of the future might look very different than they have been in the past. So tall buildings are a challenge. They're a challenge of place, material, technology. When I was a junior designer at SOM in Chicago, I had the opportunity to design this building. It's 420 meters tall, and it's in Shanghai. It was the 3rd tallest building in the world. It's called the Jinmao Tower. And a Saturday night event with my daughter, we together solved the problem for this building that was really difficult. And you can see the model that's here in the foreground. My daughter now is 29 years old, by the way, so just to get a sense of time. I have different glasses, by the way, too, and my hair is not as, my hair's a lot wider now than it was then. But what we did is we took this model, and why did we create this model? We wanted to create a natural force flow behavior in this tower, not for restraint, but actually to allow it to move during construction. So we had these big trusses that connected to the central core, then connected to the outside big columns, the mega columns, and there were 8 big columns. And what we found was when we interconnected them for lateral load resistance, we found that if we built the building from the ground up, the creep, shrinkage, and elastic shortening that this building would see between the core and the outside columns would literally rip the trusses apart because the trusses were so big. So we introduced pins into those trusses to make them behave like mechanisms using wood dowels, tongue depressors, popsicle sticks. Slots were needed and pins were needed to allow the structure to move freely during construction, attracting no force. We developed the idea into the working drawings, first starting by hand calculations, and then into the computer-generated working drawing on the left, to the shop fabricated, prefabricated units on the top right. You can get a sense of scale on the lower left of a man from SOM that was on site. The pins are in that connection. And the idea is that the pins were in place, in the image on the lower right, and then the bolts were inserted after the building had a chance to breathe. So the building today is a success. People jump off this building. People climb this building. And people do things that are kind of crazy, which by the way, I wouldn't do this. So anybody that wants to do this, fine. But this is off of the observation deck. It's the 88th floor of this building. We've activated buildings in other places around the world. So how do we bring people to these buildings in a humanistic way? The Sears Tower with these cantilevered glass cubes off of the outside of the building. So back to nature and back to the environment and how we can coexist. So like our bodies, the connections that we have they're responsive. A lot of times they're not being used. Sometimes they're being used in a way to lift materials, but always they're used in a way that has free motion. Our buildings, on the other hand, typically do not. So how can we introduce pins into our frames of our buildings to allow them to work more like your body than welding beams and columns together in a perpendicular way where it's an abnormal behavior. It's a high concentration of force. So imagine frames in the future looking like this with pins that allow for the joints to be fixed during most of the life of the structure through friction. So the curved plates have a friction material that's clamped together. We understand the coefficient of friction. We understand the clamping force. And we understand when it'll slip when the demand is high enough. It dissipates the energy without damaging the base building. That's the idea. So long range, the idea of carbon, buildings being in service is really important in the final state of our designs so that we don't have to repair them or take them down and rebuild them. So the idea is to use basic building materials that we have available in the marketplace today. Wide flange beams, hollow sections, circular sections that could act like a pin, high strength bolts, friction materials like you use in your car, in an automobile, to create these joints that allow this movement to happen when we want it to happen. We can use this idea in frames, stiffness and softness that I talked about earlier. So braced frames that at the time of a major earthquake need to dissipate energy, but when they're in their normal life, normal operations, they are there to provide stiffness of the structure until the big earthquake comes. But dissipate the energy, protect the structure through this idea of friction. Allow the joints to have circular bolt patterns so that they can rotate freely when needed. And even in structures that have shear walls, we do a lot of residential construction that is concrete. We have links that occur in the elevator lobbies typically to dissipate the energy. Use steel, in this case, in a butterfly pattern that's allowed to dissipate energy when needed. You can use these ideas in places where you run into trouble, where you have problems, when you're designing a building and you discover that you just can't quite solve it. This structure is in Beijing. The idea was to create the tallest and widest cable net in the world, 90 meters tall and 60 meters wide. And what we would do is hang a mid-height structure, which was a museum, and allow that hanging to do two things: to support the gravity loads for that piece, but more importantly, perhaps, to take the lateral load of this cable net. But we found as soon as we connected it to the top of the museum, it acted like a mega braced frame in an earthquake. It attracted so much force that we couldn't engineer the diagonals in a way. We'd put material to respond to force. We couldn't design it. We'd put more material, it would attract more force. So we needed to come up with a way to allow the building to act freely during the earthquake. So what we did is we started with the fundamentals of pulleys. The idea that the pulley, when a cable would run under the pulley and it would move from side to side, the force in the cable wouldn't change very much in motion. But our architects wouldn't allow this huge drum that we would have to create for the size of the cable that we were using. So we came up with this idea of pins, 4 pins with plates to allow the same motion to occur. We took those models and created the in-place structure, which could be used to resist these lateral loads from wind on this large cable net, but also provide motion when needed in the large earthquake. So it is still today the largest cable net in the world, and it's designed to move, even though when you see the building on the outside, you may not see the connection, but from the inside, you certainly can. So there's a couple of places where we've written about the work. One is in a book for Detail. It's a German company that publishes a lot of architectural details, but they asked us to do a book on structures. And then a book on tall buildings that came out of work with schools, Stanford University in particular, about the idea of structure as architecture in tall buildings. And what the book does is it takes you through the steps of the site, where not much is known except for the natural characteristics, all the way through some more of these advanced ideas that we're talking about today in terms of the impact of nature on design. So there are resources that are available if you're interested. It happens at great scale. It's not just at the top of your head or the growth pattern of a plant. These geometries are not random. They're important, and they're embedded in motion, and they're embedded in the way we see dynamics. So in simple wave theory, as you touch that string and change the boundary conditions, you can see that there's a different dynamic characteristic, right? Imagine that everything is in motion. Everything. We're in motion. This building is in motion. The planet's in motion. That's the philosophy. So 50 years ago in San Francisco, it was the summer of love, okay? I wasn't there, actually. I was pretty small. But anyway, this whole freedom of ideas, right? Freedom of form, motion. That's what we think is important. And that's what we think actually can get into buildings that are not super tall. Buildings that are shorter. In this case, in Long Beach, California. 2 fairly short office buildings. Simple in plan. Core systems, columns, open office space, structures that consist of shear walls, and post-tension slabs between the shear walls and the columns. But we wonder, what about all these ideas for tall buildings could maybe be appropriate here? And what about wave theory? Typically when we post-tension these slabs in our buildings, and many of us in the room are involved with this, it's a linear approach with cables, right? They drape vertically, but usually in the horizontal plane, there's not much variation. And this is what we've been doing for literally 60 and 70 years in our buildings. But if you look at the force flows, they're much more organic. They're like flower patterns. They're not linear. It's not point to point. This is the most efficient path. And if you superimpose an idea of where the structure might be, all of a sudden something beautiful appears, and it's not a straight line. So wave theory and placement of cables that you can imagine that are now in the concrete, in one direction, then another, and then the combination of the two, and then the other direction, the other, combination. And when you combine them together, something really beautiful emerges. It's a pattern that looks more like Vesica Pisces and the origins of the universe. And I'm trying to pull this all together. It seems like a stretch, but it makes sense that the mathematics have got to be the same. So you can take this and you can create grids of placement of material, elevationally and in plan. And what you see are these intersecting circles that form the structure. You can reduce the material by almost 30% when you use an idea like this. It's important for us to think about in our designs. There's a building under construction right now in San Francisco. It's a fairly basic floor plan. It's a residential building with a core in the middle and a series of columns around the outside. When you look at this analytically, though, you find that the state of stress in the slabs is not linear. It's much more organic. The red spots are the hot spots. That's where the shear typically is the highest. That's where the forces are flowing. That's where we need to map the structure. So this idea of looking at it and interpreting it in a way that draws, let's say, from the analysis model what these cables may look like is where we believe the answer lies. So taking that force flow and creating a pattern like the one on the right with the cables inside the slab reduces the material by 25%. Describing structure like it's a musical instrument. So in plan, the idea of the cable placement, but also in elevation like the staff, like a musical staff, so that the contractor can see in plan and in elevation every cable in every position as they lay out the cables in construction. So we work with outside architects as engineers. It's not just SOM, and there are a few important ones around the world that we're working with right now, including Peter Zumthor, and also Grupo Sordo Madaleno here in Mexico City, on important work that we hope that we can add some value in terms of the engineering. This example I'll show you is one that looks at structure from a way that is not conventional. And this is the Los Angeles County Museum of Art, currently under design and soon to be built in Los Angeles. Peter Zumthor, the architect from Switzerland. Peter is somebody that looks at material in a very substantial way. He looks for inspiration. He looks for ideas of placement of material within structure that is efficient, it's smart, it's holistic. In this case, a reinforced concrete structure with very ambitious cantilevers and long spans. And we too look for organic ways of creating structure. In this case, the least energy is where the lines of this crack pattern exist. But if you reverse it and think about, instead of relieving the structure, maybe that's the area where the highest concentration of structure might exist. It exists elsewhere. If you look carefully, right, in water patterns. And so what we did is we tessellated the structure. And we created an idea that takes Voronoi, a natural placement of material, and creates vertical structure first, walls that are interconnected with walls that would exist on the occupied floors, and arms that would reach from that, and then fingers that would reach from that respect this Voronoi pattern. To create spans in areas of efficient ribs that would be able to span the cantilevers and long span areas. And then ideas of post-tensioning in the slabs themselves, right? So this, again, this organic pattern of force flow and responding to where the demand is highest and where it's least. And it appears in places that we think are important, like the Venice Biennale. So these drawings that talk about the engineering of a building that's complicated are celebrated along with other art pieces that are part of this exhibition. So finally, back to this organic nature in art. We think that the engineering concepts that we're developing are appropriate for things like urban planning. And you can imagine that this is a structure with certain sizes of support, or you could imagine that it's certain densities. In this case, the highest density with the largest area of support. Using that same idea of optimization of material, imagine it's people or vehicular movements rather than structure. It's based on the same idea. And what you find is that the flows that go from point to point, and we saw that just before in terms of the way people use space, is not necessarily linear. So these patterns we think are the most efficient ways of perhaps planning cities of the future. We can distort the plan, distort the idea by moving, let's say, a secondary center closer to the middle. And all of a sudden there's a disruption to that flow, but this is an organic response to that change.
Oh, thank you.
Why?
Okay, hold these.
Milkshakes.
There we go.
How many milkshakes did you buy?
God.
One strawberry, one vanilla, and one chocolate.
Is that what you ordered, Jack?
One of each.
Yeah, but your food still needs to cook by the rain or
I know that. I'm just saying a bit. I know that. Yeah, I'm really sorry. But can we get a move on? That's fucking good then. Nothing better than fucking McDonald's milkshake. Cheers, mate, for doing this. Cheers, mate, for doing this. Appreciate it. That's everything. Wicked. Drive. Let's go. Stay outside.
My love and I. A ship there is, and she sails the sea. She's loaded down as deep may be, but not so deep as the love I'm in. I know not if I'll sink or swim.
So awareness and being aware that there are environmental changes, sitting in automobiles with running engines or using material and structures that's not efficient is all part of this complex idea that we need to make change. And if we don't make change, then there's a backup plan. It's not a good backup plan, but there is a backup plan. So imagine that the sea level is going to rise significantly. And imagine San Francisco and the Golden Gate. What to do if we have 2 meters of sea level rise and storm surge? Well, we looked at the Golden Gate Bridge and we looked at the bay, and we developed an idea, just in case, where you could actually create a structure that would lie on the base of the bay, allowing ships and sea life to move freely for most times. But when the sea level rises and there's surges, the idea of deployment of a structure that could come off the base and help to protect the bay from the surges is an idea. It's a response. It's not an active response, it's a passive response. It's a what-if response. But using tension in the structure, using a baffle system at the surface that would be deployed with air to help us to protect the built environment. So I challenge all of us, me and all of you, as to whether or not this is acceptable. The idea of inventing ideas that protect us but are not proactive, that are reactive. So someday we may see the Golden Gate Bridge like this, but I'd argue this is not where we want to go, that we want to deal with the ideas and the developments much sooner than this. So that's what I have for you today. Thank you for listening.
Bueno, can you use your thing? Okay. Sí, muchísimas gracias. Está poniendo su traductora, Mark. Muchísimas gracias, Mark. ¿Ya está? ¿Ya estás? Are you listening? No. ¿Ya? Ok. Bueno, pues realmente un motivo más para estar preocupados, pero sí, por otro lado, estar animados a seguir buscando soluciones para todos estos problemas. Agradeciendo muchísimo la generosa participación del ingeniero Mark Sarkisian acá con nosotros, nos iremos a comer al rato. La presidenta del Colegio de Arquitectos de la Ciudad de México quiere hacer un reconocimiento por su participación. Muchísimas gracias, Mark. La foto. Quiero agradecer también a Noemí Guerrero Lara, que ha sido nuestra coordinadora. Ella es alumna de la especialidad de Gerencia de Proyectos en la UNAM. Muchísimas gracias, Noemí. Y bueno, pues creo que ya es hora de irnos a comer, agradeciendo nuevamente a Mark. Sí, claro. Y si puede venir por la derecha. Les recuerdo que a las 4 de la tarde tenemos la conferencia del arquitecto Javier Sordo Madaleno Bringas. Va a estar hablando de su arquitectura aquí en este mismo lugar a las 4 de la tarde. Les agradeceremos su presencia y pues